leveraging deep learning for accurate classification of Leptograpsus crabs based on morphological measurements. Accurate species classification is essential for effective ecological management, supporting ecosystem monitoring, population tracking, and early detection of imbalances. By identifying at-risk species, classification efforts bolster conservation, allowing resources to be directed where most needed. AI automation, specifically using Convolutional Neural Networks, CNNs, enhances the speed and precision of species identification over traditional manual methods, enabling scalability in biodiversity studies. This interdisciplinary approach between AI and ecology showcases the potential of deep learning to provide impactful insights for conservation and decision-making. Species classification is a cornerstone of biodiversity monitoring, enabling us to track ecosystem health, detect imbalances, and respond to ecological changes. It also supports conservation prioritization by identifying species at risk, facilitating efficient resource allocation, and aiding habitat management to address specific species needs. Additionally, accurate classification plays a role in controlling invasive species and promoting sustainable resource management. By recognizing shifts in species dynamics over time, we gain early warnings of ecosystem degradation and improve our understanding of critical species interactions, such as competition, predation, which are fundamental for ecosystem stability. Next, we'll look at automation. So this research uses CNNs to classify Leptograpsus crabs based on morphological features, automating and enhancing classification accuracy and efficiency. Compared to manual methods, AI-powered classification enables scalable biodiversity monitoring and supports conservation efforts by providing precise and rapid analysis. This highlights AI's transformative role in modern ecological research. The interdisciplinary approach in this research integrates AI, specifically deep learning, with ecological science to classify Leptograpsus crabs more accurately. By combining AI techniques like CNNs with ecological methods, the study enhances biodiversity monitoring and conservation efforts, providing more precise data analysis that supports ecological decision-making. This collaboration illustrates the transformative potential of applying advanced AI to solve complex ecological challenges. The study addresses the need for accurate species and sex classification of Leptograpsus crabs, as traditional methods are time-intensive and error-prone, hindering large-scale monitoring. Using a CNN, the research achieves high accuracy rates, 97.5% for species and 95% for sex classification, illustrating deep learning's potential in biological classification. The dataset includes morphological measurements, for example, the carapace width, length, body depth, from 200 crabs, equally divided by species and sex, collected in Fremantle, Western Australia. This data supports feature extraction and model development, showcasing the morphological diversity essential for accurate classification. We utilize CNNs for species and sex classification. CNNs are ideal for tasks that involve pattern recognition and image analysis, as they can automatically learn features from raw input data. The model architecture consisted of two 1D convolutional layers with 32 and 64 filters respectively, followed by a ReLU activation function. These layers capture inaccurate patterns in the morphological data. A flattened layer was used to convert the 2D feature map into a single long feature vector, followed by dense layers for decision making. The model ends with a single neuron with a sigmoid activation for binary classification. The dataset was split into 80% for training and 20% for testing. The model was trained for 50 epochs using the Adam optimizer, which efficiently adjusts learning rates during training with binary cross-entropy as the loss function. For this binary classification task, binary cross-entropy was employed as the loss function, resulting in 97.5% accuracy for species classification, 95% for sex classification. Shapely additive explanations, SHAP, analysis was used to enhance model interpretability, making it more transparent for ecologists and conservationists. SHAP revealed that the carapace width and the carapace length were the most influential features in the model's predictions. Summary plots showed how different values of these features impacted classification decisions, aligning AI insights with biological knowledge. This interpretability fosters trust in AI-driven conservation efforts by clarifying which morphological features are critical, ultimately supporting informed decision-making. Early stopping was implemented to prevent the model from training too long and starting to memorize training data rather than learning generalizable patterns. Training was halted when validation loss stopped improving, ensuring that the model didn't overfit on the training data. A dropout layer of a rate of 0.5 was included in the model architecture. This layer randomly deactivates 50% of the neurons during each training iteration, which prevents the network from becoming too reliant on specific nodes. And this encourages the model to learn a more generalized representation of the data rather than being overly sensitive to particular features. A 10-fold cross-validation approach was used to validate the model's performance on different subsets of data. This approach splits the dataset into 10 parts, using 9 parts of training and 1 part for validation iteratively. It ensures that the model is assessed on a variety of different splits of data, enhancing its generalization capacity. The model's architecture was deliberately kept simple by limiting the number of layers and parameters, which reduces the risk of overfitting. Excessively complex models can overfit by learning inaccurate noise patterns specific to the training set, but a simpler model helps focus on the core patterns in the data. The learning curves for both training and validation accuracy were analyzed to monitor overfitting. A divergence between training and validation accuracy indicates overfitting, and as such, visual analysis provides insights into adjusting training parameters in real time to prevent overfitting. The implementation of these techniques effectively minimized the model's overfitting. The validation and training learning curves remained close, showing that the model was able to generalize well to unseen data. The cross-validation yielded an average accuracy of 99% plus or minus 1.22%. Further demonstrating the model's robustness across multiple subsets of the data. The CNN achieved high effectiveness with 97.5% accuracy in species classification and 95% in sex classification, as confirmed by confusion matrices showing minimal classification errors. For example, species classification correctly identified 39 out of 40 instances. The ROC curve values were excellent, scoring 1 for species and 0.99 for sex classification, affirming the model's strong discriminative power. With 10-fold cross-validation yielding an average accuracy of 99% plus or minus 1.22%, the model demonstrated robust generalization across data subsets. Metrics such as precision recall and F1 score highlighted balanced performance with few false positives and negatives, underscoring the model's reliability and accuracy in practical applications. The study demonstrated that convolutional neural networks are highly effective for classifying Leptograpsus crabs based on species and sex, leveraging key features like carapace width and length. Despite the model's success, challenges such as reliance on a limited data set were noted, which may impact its generalizability. Nonetheless, the incorporation of SHAP analysis ensured interpretability, linking AI model insights with biological understanding, thereby validating the robustness of the approach in supporting biodiversity research. The implementation of AI in this research highlights its potential for scalable applications in biodiversity monitoring and conservation, providing efficient, automated solutions for species classification. By integrating AI models with remote sensing and environmental sensors, real-time monitoring of ecosystems becomes feasible, which is crucial for conservation. Furthermore, this study emphasizes the need for interdisciplinary collaboration between AI experts and ecologists, as AI-driven tools can enhance ecological understanding, improve resource management, and ultimately support broader environmental protection efforts. The study successfully applied CNNs to achieve high accuracy in classification by sex and species, demonstrating the efficiency of deep learning for biological classification tasks. The combination of advanced AI techniques, robust feature importance analysis, and overfitting prevention measures contributed to a reliable model performance, with cross-validation and SHAP analysis supporting interpretability and generalizability. This research not only contributes to ecological studies, but also highlights the role of AI in enhancing biodiversity monitoring and conservation, paving the way for automated, scalable solutions in environmental research. The impact of this research on the field of IT is significant, showcasing how AI and machine learning models can be effectively adapted for real-world interdisciplinary applications such as biodiversity conservation. It emphasizes the value of using explainable AI tools like SHAP to ensure transparency and trust in model decisions, which is essential for wider adoption of AI in scientific domains. Furthermore, the successful use of CNNs illustrates the broader capability of IT to address challenges in data-driven environmental monitoring, supporting advancements in AI-driven ecological tools and promoting their integration into real-time decision-making systems for sustainable resource management. Thank you.